Two servers, separate machines, separate kernels, one container on each. Now ping one from the other using nothing but an IP address. It answers almost immediately. No NAT, no port forwarding, no config file anywhere that says how that is supposed to work. That is not something Linux hands you for free. Somebody had to build it, so let's go find out who and exactly how. Kubernetes never actually described how the network should work. It states three rules and then refuses to say another word. Rule number one, every pod gets its own IP address. Rule number two, every pod can reach every other pod on any node with no network address translation in between. Rule number three, agents on a node, things like the kubelet, can reach every pod on that node. That's it. That's the entire specification. And Kubernetes ships exactly 0 lines of code that makes any of it true. So it defines that contract and hands the entire problem to somebody else. The CNI plugin, that is a container network interface. Calico, Flannel, Cilium, they're all just different answers to the same three sentences. Start with rule number one, because it is a rule people most underrate. Pull up your pods and look at the IP column. Every single pod has its own address, and if you look closely, the addresses are grouped by node. Node 1 hands out 10.244.1 dot something. Node 2 hands out 10.244.2 dot something. Each node owns one slice of the pod network and allocates out of its own slice. No coordination, no collisions. This is not natted Docker bridge where every container on every machine quietly thinks it is 172.17.0.2. The pod's IP is the address other pods can actually dial. It's real and it's routable across the whole cluster. So go and look from inside. The pod has an H0 and H0 is holding the exact IP the API server told you it had. It also has its own routing table, its own ARP cache, and its own IP tables rules. This is network namespace. A namespace is just a kernel handing a process a private copy of the whole network stack. Every container inside one pod shares that single namespace, which is exactly why containers in the same pod talk over localhost and why two of them can never both bind port 8080. That H0 has to plug into something. Here is the trick, and it is a part almost nobody actually goes and looks at. SSH onto the node, run IP link, and you will find interfaces you never created with something, and back inside the pod H0 called itself H0 at F9. Those two numbers are pointing straight at each other. A with pair is a virtual Ethernet cable and it exactly has two ends. Whatever you push into one end comes out of the other end, always, and that is the entire contract. The kernel builds the cable, leaves one end on the node, shoves the other end into the pod's namespace and renames it H0. The pod's network card is one half of a cable, and that is the entire illusion. Now you've got a pile of loose cable ends lying around on the node, so the CNI plugin plugs every single one of them into a bridge. CNI 0 is a software switch living inside the kernel and it behaves like a dumb layer 2 switch because that is all it needs to be. It carries the gateway address for that node's pod subnet 10.244.1.1. Two pods on the same node, the packet leaves H0, crosses the cable, hits the bridge and switches straight back into the other cable. Pure layer 2. It never even touches the node's routing table. The hard part is the other machine. Nginx on node 1 wants to reach 10.244.2.7 and that address is not even on its bridge. So the packet reaches the bridge, finds nothing and gets handed up to the node's routing table. And the node has a route sitting right there. 10.244.2.0/24 goes to node 2. Every node knows which node owns which pod subnet. And how it comes to know that is the only thing the CNI plugins genuinely disagree about. Flannel wraps your packet in a VXLAN header and tunnels it across the node network. Calico skips the wrapper entirely and just speaks BGP, so the routes on your nodes are the real routes. Cilium does the whole thing in eBPF, and we are going to come back to that because this is where it gets really interesting. But the shape is identical every time. Find the node, get the packet there, unwrap it into the node's bridge. So here it is, the entire path end to end, nothing left out. H0 with bridge routing table, the node's NIC, the wire, node 2's NIC, node 2's bridge with H0. 10 hops, 0 NAT, and the source IP that arrives is the exact source IP that left. That is rule 2, which is satisfied. And if that just made something click, subscribing is how you get the next one. Anyway, there is a problem with everything I just showed you. Pods die constantly, and every time one comes back, it comes back with a brand new IP. So nothing can hardcode a pod IP. You would be chasing a moving target forever, which is why you get a service and a cluster IP. That IP is stable. It will not change for the entire life of the service. And also it is completely fake. There is no interface anywhere in your cluster that holds that address. No pod owns it, no node owns it. Nothing in your cluster will ever answer an ARP for it. So now you have a packet addressed to somewhere that does not exist about to leave a pod. It gets rewritten before it ever leaves the node. kube-proxy watches the API server and programs the node's IP table's NAT table to match. This is what that actually looks like on a real cluster. Your packet leaves the pod with a destination of 10.96.123.45. It hits the kube services chain, matches one rule, and gets DNATed to an actual pod IP. The kernel picks one of the backing pods, more or less at random, and rewrites the destination in place. And the pod that answers has no idea a service was ever involved. ClusterIP is not a place, it's a lookup key that gets swapped out mid-flight. And all of that works right up until it doesn't. iptables is a linear chain. The kernel walks it top to bottom until something matches. And the lookup is only half of it. Every connection also gets an entry in conntrack, and that table has a hard ceiling you will eventually hit. 5 services is fine, but 5,000 services, and you're walking tens of thousands of rules for every single packet. And it gets worse because kube-proxy cannot patch a single rule, it rewrites the entire whole table. On a large cluster, one single change can take that node seconds to converge, seconds on the data path. And that is not a tuning problem, that is a wrong data structure. Kubernetes did try to fix this. kube-proxy has an IPVS mode that swaps a linear chain for a real hash table. And it does help, but the rest of the data path is still IP tables. So you have moved the bottleneck but not removed it. So eBPF is how you get out of this. You load a small, verified program straight into the kernel and you attach it to the packet path. Cilium uses that to replace the entire IP tables chain with a hash map. Service lookup stops being a walk down a list and becomes a single constant time lookup. Same load balancing, same DNAT, no chain anywhere inside. It can even do the rewrite down at the socket before the packet is ever built. And because that program already sees every packet, you get identity aware policy and full flow visibility essentially for free. Same three rules, completely different machine underneath them. So, pods get real IPs, veth pairs plug them into a bridge, the node's routing table finds the right machine. And services are a useful fiction the kernel maintains on your behalf. None of it is magic, it's namespaces, cables, a switch, and a routing table. The only reason it feels like magic is that CNI does all of it before your container's first line of code ever runs. That's it for this video. Thank you. Please consider subscribing and I'll see you in the next one. Thank you.